I'm presenting my research on integration of 2D materials in resistive switching devices for the Nanomaterials and Nanotechnology Web Congress. And if you are familiar with the topic, this will feel like a literature review. So first I will explain my abstract with this poster and then move on to the research itself. For people only interested in the summary, this first couple of minutes should be enough when they are watching this recording. So as you know, the interest on 2D materials is growing every day due to the discoveries of their unique benefits on many areas. Their potential became apparent thanks to the research on graphene as well as methods of synthesizing, transferring, detecting, and manipulating all layered van der Waals materials. As a description, nanosheets have micrometer dimensions in plane and nanometer thickness. Many researches have been done on semiconductor technology to have an economic and fast solution of thinning silicon for integrated circuits. However, as traditional silicon-based technology is reaching its physical limits, 2D materials offer a more efficient solution for this. Since having low dimensions is important on especially electronics applications, I was interested in choosing the right material to improve device properties. Many studies investigated physical and chemical properties of 2D materials to use in insulators, semiconductors, metals, and so on. And since the discovery of memristors, it is revealed that 2D materials can be used in resistive switching devices. But fabrication of such devices require research on synthesis and transfer of 2D materials used for them. According to the research, especially for large yield synthesis, chemical vapor deposition is the most suitable option. Unfortunately, although few 2D material vendors exist, currently the large-scale manufacturing is in early stages because the largest customer base is research and development laboratories, which is not enough. And initially, among others, boron nitride ended up in a unique position due to its similar properties with graphene, except having a large band gap on its main forms. And my work is focused mainly on boron nitride with hexagonal structure, or HBN for short. So in this paper, the review of 2D materials with the focus of HBN and resistive switching RS memory devices were conducted. Also, their fabrication and transfer methods for the purpose of technological advancement on current applications is examined. The resistive random access memory, or RRAM for short, seems like the most efficient alternative as a non-volatile memory here. The results of this research show that HBN-based RRAM is the best current alternative to work with. However, as always, future improvements are still expected. So now we get into more detail. I will simply follow this contents, and there might be parts I repeat myself since the abstract was sort of a summary, but I hope I will not bore you. So let's start with a little introduction. We are talking about nanosheets here, which have micrometer dimensions and in plane, and their thickness can be around nanometers. And 2D materials and methods of synthesizing, transferring, and manipulating them are all being studied right now. This is because their unique structures create useful properties for many electronics-related applications. One of the most important potential of 2D materials is in the resistive switching memory devices, which were gained attention after the discovery of memristors. Here, RRAM is suggested to be the most efficient alternative non-volatile memory. And HBN-based RRAM is the best current alternative to work with, even though future improvements are still necessary. Fabrication of such devices require the research on synthesis and transfer of 2D materials used for them. And for large yield synthesis, here chemical vapor deposition is defined as the most suitable option. And this study in 2004 on graphite monolayer or graphene started a research period on 2D electronics by describing their properties on molecular level. Most studied elemental 2D materials after this include paraffin, silicene, germanium, stannine, and phosphorine. And other popular 2D materials are these, including HBN, mostly due to its insulation properties and chemical inertness. All 2D materials are composed by covalent bonded layers held with weak van der Waals interactions to form 3D crystal. And the weak van der Waals does not contain dangling bonds. With this structure, combination of 2D materials can stack in sequences to create new van der Waals heterostructures. And these heterostructures may even show combined functionality of the individual layers. My focus, BN, is isostructural to carbon and made of chemical compounds consisting equal numbers of boron and nitrite, which are produced synthetically since it's not found in nature. BN allotropes are shown here in the figure. To understand the concepts better, single-layer HBN is usually referred as BN nanosheets, since its aspect ratio is small, and if it's higher, then they call it BN nanoribbons. And as you can see, individual HBN basal plane is honeycomb structure made up of ring units of borazine. About the properties of 2D materials, they are very thin and self-passivated, and they have high mobilities even at the atomic thickness limits. BN nanomaterials have even more unique properties. They are usually resistant to wet and dry oxidation, for example. And the major difference between BN and graphene is their electrical conductivity, since graphene is a semi-metal and BN sheets are insulating. More specifically, bulk HBN has these advanced properties. And due to their large band gap, surface flatness, and freedom from the surface charges, it can be used as substrate for many 2D nanomaterials in electronic and optical applications. They may even advance the device performances of 2D van der Waals solids. Moreover, HBN is very suitable for resistive switching because some devices can use it as active layer. Large surface-to-volume ratio of 2D materials is useful for energy storage and sensing applications. They can be used in many other markets also. 2D materials are being implemented in several components. They even show promise as components of IoT hardware like switches, photodetectors, sensors, piezoelectric materials, and so on. Many specific examples can be given, like graphene could serve as the buffer layer between 2D semiconductor and the metal for contact improvements. But BN depends less on thickness than graphene. Therefore, HBN is more suitable for high temperature applications. Currently, HBN is mostly used as UV emitter, insulating thermoconductive filler, pencil leads, as well as in many commercial powdery, skincare, and cream cosmetic products. It can be assumed that many future markets will use 2D materials if the improvements on cost, mobility, and scalability can be achieved. So RS for non-volatile memory is studied widely because it can be scaled down to less than 10 nanometers. Also, it can offer many features, and it has a high potential to replace charge-based memory devices. Therefore, materials exhibiting RS behaviors, such as metal oxides, organic polymer, and 2D nanomaterials were examined. Among the alternatives, mainly resistive random access memory, RRAM, or sometimes VRAM, seems to be the most promising one. RRAM is a simple structure with high speed, high endurance, large capacity, low power consumption, and high scalability. Currently, RRAMs use a metal insulator metal structure to store information where the insulator, usually a transition metal oxide, allows cyclical electrical RS. However, any single RRAM is not capable of showing all these high performance qualities simultaneously. To solve this issue, the metallic or insulating films can be replaced by some 2D materials and provide additional capabilities to the devices like flexibility and transparency. In general, RRAM devices are called memristive devices. Regardless of the device material and physical operating mechanism, two-terminal non-volatile memory devices based on RS are called memristors. Memristor, as the so-called fourth basic circuit element, behaves like a linear resistor with memory, but shows nonlinear characteristics. It's a two-terminal electronic device without an internal power source, capable of switching between two resistances upon application of a voltage or current. High-performance memristive devices are wanted because of many advantages seen here, but large-scale TMO-based memristive devices have several challenges, as you can see here also. Due to their superior physical properties, 2D materials can be used instead to solve these issues and achieve more complex functionalities. The fabrication of 2D RS memories are highly dependent on the synthesis and transfer of used 2D materials. To give some insight, most solid-state memories in nanoelectronics have an internal matrix organization within the integrated circuit chip, with a switch realized by a MOSFET on each node. Also, preparation of ECM memory cells is based on thin film techniques for nanostructures, and poor adhesion between conventional switching materials and substrates in resistive memories causes the repetitive bending, which results in detachment and cracking. For the synthesis methods, optimal growth substrate varies with the chosen 2D material. This choice of growth substrate impacts fundamental mechanisms. The synthesis of uniform large areas, single crystal films over substrates, which epitaxy or templating is required to orient domains, is still a challenge. But understanding the interaction between substrate and 2D material, as well as the interface properties, are very important for quality. To have a full potential heterostructure, techniques for controllable synthesis over large areas where interlayer interfaces are maintained must be developed further. So most known synthesis methods are exfoliation methods, which include several versions, mechanical being the most popular one. They can be also dry or wet. Simple adhesive tape peeling, called micromechanical cleavage method, or the Scotch tape method, is repeating the process of peeling off layers with adhesive tapes and attaching to a substrate. This is one of the least scalable methods used for obtaining atomic HPN sheets, especially for large-scale applications. CVD is the most promising method for scalable growth of high-quality sheets. There are many aspects to consider, and there are many types of it, but basic version is pretty straightforward. The right gases are put in a reaction chamber with an ambient temperature, and as they contact with the heated substrate, the reaction happens. CVD is a scalable and reliable technique which has a potential to achieve large area HPN samples with excellent layer number selectivity and controllable quality. This figure here shows two representations of HPN synthesis with a CVD furnace. CVD synthesis of HPN on several substrates, like metals and insulators, offers new possibilities for device fabrication. And it is also tailoring on properties by adjusting parameters such as growth temperature, process pressure, gas ratio, and so on. After the material synthesis, a transfer method is needed in order to use 2D materials in certain applications, as well as RS medium. High-quality large area assembly is possible with transfer of 2D materials by one on top of another or using one to pick up another. However, interactions after the transfer and impact of different substrates can have problems like roughness or contamination, which can cause unintentional doping, strain, or defectiveness. Therefore, this surface must be engineered carefully for stable and reliable results. And although wet transfer is easier to do, results may have imperfections, causing undesired effects on some properties of 2D materials. Dry transfer methods were developed to resolve those issues, and they use different materials along the way. The wet transfer of grown 2D materials was developed as a more controllable and scalable process due to Scotch tape method's limits on large-scale manufacturing. But during the wet transfer process, thin 2D materials coated with polymer handlers are dipped into wet chemical etching solutions to separate them from the catalyst substrates. Then, the polymer and 2D material stack is detached from the substrate by the target 3D substrate. And the polymer handler is transferred to the target substrate, where it is chemically dissolved in an organic solvent. Dry transfer is a more flexible technique to explore heterostructures, which is critical to ensure a uniform and repeatable transfer with minimal impact on the 2D material. It does not require them to be exposed to organic solvents. In dry transfer, flakes of the 2D material are fabricated on a polymer sheet. Then it is transferred onto another material, like exfoliated HPN on a silicon substrate, without dissolving the polymer sheets by organic solvents. Physically, RS is related to the motion and interaction of oxygen ions and vacancies. Therefore, especially materials with wide band gap, high electrical resistivity, and high thermal conductivity can offer excellent switching performance for the RS memory. This figure shows the schematic of devices made from these materials with their switching characteristics. As mentioned before, the performance of MIM-based RS devices may be enhanced with layered 2D materials. More specifically, HBM can be a good solution for enabling the fabrication of RRAMs and other logic devices since it can generate essential device functionalities, like the generation of electrical fields and capacitance effects. Also, atomically thin HBM can be used to engineer a new class of 2D RRAM device because it is a 2D dielectric showing reproducible RS. It is possible to develop a complete family of scalable RRAM devices using multi-layer HBM as the active RS medium. Basically, HBM-based RRAM devices have very good non-volatile memory performances, including low set-reset voltages, high on-off current ratio, good endurance, and very low overall variability. This figure shows the schematic of an HBM-based device with the TEM image of the cell and electroforming process of HBM with switching characteristics of the device after the process. So, to sum up, this research was prepared as a review on 2D materials and RS memory devices, as well as discussing the best combination of them. The review on 2D materials included many titles, but the focus was given to BN structures rather than popular carbon-based materials. RS memory were also explored, and RRAM was chosen more favorable as a non-volatile memory. RS of 2D memories review was focused on characteristics of HBM-based RRAM, which suggests that currently this is the best solution available. So future studies on this topic will hopefully discover more, especially van der Waals heterostructures should be studied in more detail to achieve more stable and reproducible results. And with the advancements on these technologies, it is possible to have improvements in many electronics-related areas. So here are the references I use in this study for anyone interested. Now, thank you all for listening.